I am here from Stanford and I'm still on California time, so it's about 4 o'clock in the morning for me, so you're going to have to apologize if I'm a bit... Okay, so here's an outline of my talk. I've tried to pack in quite a lot of stuff here, so we'll see how much we can get through. Hopefully we can get right to the end, but I don't know, we'll see. Depends how quickly I can talk. So the first thing is going to be, what do we mean by net energy? So actually, first a disclaimer, I'm not a physicist, much to my delight, sometimes chagrin, other times. I'm not a physicist. I'm a physicist, not an economist, so I think of energy as a currency. So whenever I use some of these words, cost, spend, expensive, afford, debt, profit, I'm talking in terms of energy, not in terms of money or finances. Okay, so the first topic, what do we mean by net energy? Here's a good definition from John Peet. It's basically the amount of energy delivered to the economy less the amount of energy required to get it there. So here's an illustration of this. The energy sector puts out some gross amount of energy. Some energy is needed by the energy sector in order to produce that energy, both in terms of direct inputs, so fuels, but also in terms of indirect inputs like materials, capital, ancillary services, all of this kind of stuff. And if you take away that feedback energy from the gross energy, you get the net energy. Just as a little point, the gross energy is what is measured by most agencies, so the UN, EIA, IEA, BP, Shell, whoever you want to talk about. Here we've got a plot for a single power plant, but this could be any kind of energy project. And basically below the line in blue, we've got energy inputs, and above the line, we've got energy outputs. So the first kind of input that we need to do is we need to build this plant. So we've got this construction energy. Then once the plant is up and running, it starts producing energy, which is in yellow here. But there's some operation and maintenance energies, and maybe some energy associated with the fuel cycle, if this is nuclear or fossil fuels. That goes on for the lifetime of the project, and then at the end, we've got some decommissioning energy. Okay, so the net energy of a power plant depends on two factors. The first is how much energy it takes to deploy each unit of capacity. So this is called, in life cycle analysis, this is called the cumulative energy demand. It's also called the gross energy requirement in some circles. Basically, this is energy cost. I'm going to talk about this. And then the second factor is energy output. How much energy does each unit of capacity produce? And we've heard a lot of talk, especially from Professor Jefferson this morning, about the capacity factor. So each unit of energy, each unit of capacity will produce a certain amount of energy. This is also called the load factor as well. And then here are some typical values for a lot of the electricity technologies. Okay, so now we've got these different ideas, we can start to define some useful net energy metrics. And the first is an energy return ratio. So over the lifetime of our project, how much energy will our initial investment pay back to us? And the most famous of these is probably energy return on investment. So it's defined as the energy out, which was the yellow block, divided by all of the energy inputs, all of the blue blocks, over the lifetime of the project. And here are some more typical values for electricity production. The second useful metric is energy payback time. So how much energy, how quickly will our energy investment be paid back to us? And this is all of the energy inputs, and so those are the blue blocks, divided by the rate of energy delivery. And this is normally measured in years, though sometimes in months for some technologies. And here are some typical values again. And I think we've had some mention that PV is around about 2 years, and we'll come back to that. Okay, why is net energy important? Okay, so the purpose of the energy sector is not just to run the energy sector. We also want it to produce some energy for society in general. And historically, the requirement for the energy sector to run its own processes has been very low, less than kind of 5% of gross production. So lots of energy has been available to society to do the things that we like to do. As Amory Lovins points out, we want energy for hot showers and cold beers and fast cars, not just to run the energy sector. Okay, so what happens if the energy requirement for the energy sector changes? Well, if it increases, as you can see from this kind of illustration down at the bottom, then there's less net energy available to society. So that may slow growth of the economy, which is a recession, or it may even cause contraction of the economy, a depression. Okay, so there's a little bit of difference between static and dynamic analysis. So a metric like EROI is measured over the whole lifetime of a project. So it may actually disguise the costs when you're trying to rapidly build up an industry. The timing of these energy inputs and outputs matters, and especially so for renewables. A lot of the costs come up front. You have to pay those before the projects start producing energy. And we'll see the effects of that now. So this is a little thought exercise. We're going to model a renewable energy industry scaling up. And it's going to be growing at 100% per year. So every year it's going to double in size. And all of the costs are coming up front. So there are no operation and maintenance costs. It's just all upfront costs. And the energy payback in this particular instance is 2 years. So in the first year, we build out one plant. In the second year, that plant starts producing energy, and it produces half as much as the initial investment was, because the energy payback time is 2 years. We also build out 2 more plants. In the third year, those 2 plants from the previous year come online and they start producing energy, but we build out 4 more plants. And then year 4 and year 5, the pattern continues, and we can see that the energy inputs are increasing at a faster rate than the energy outputs. So the conclusion is that this industry, if it continues growing at 100% per year, is going into deficit. It's running up a debt. But no industry is going to continue growing exponentially forever. So this is kind of looking now at the timescale of decades. And we're modeling this industry growing up to some limit. And you can see the gross output here is growing up to some limit. So that's the yellow portion. And then the net energy output is this dashed line, which initially comes negative. Then as the growth rate slows, it turns and starts. And there's some point at which it becomes, instead of being a net negative electricity producer, it crosses over and becomes a positive net energy producer. And we call that year the break-even year. Now, up to that time, the industry has been running a deficit and built up this energy debt, so it's required this energy subsidy. After a certain number of years of positive energy, net energy production, it's going to have made enough energy to pay back that energy subsidy that was required for its initial growth, and we call that the payback year. Okay, we can recast this whole thing in terms of this map here, and I'm going to be referring back to this map, so it's a good opportunity to kind of explain it well. So on the left axis, on the vertical axis, we've got growth rate. So this would be growth rate of the industry. Along the bottom axis, we've got energy payback time in years, and here we're assuming 11.5% capacity factor, and I'll come back to why we're assuming that in a minute. But that gives a very good one-to-one correspondence between the energy payback time in years and the energy cost of an energy technology in kilowatt hours per watt peak. Now we can divide this space into 2 different regions. We've got the green region, which is an energy surplus. So if we've got either a low growth rate and a low energy payback time, we'd be very far into this energy surplus region. So the industry is consuming very little of its own production. Or we can be in this energy deficit region, which is the red region, in which case the industry is consuming more than its gross energy output. It's requiring a subsidy. And in between those 2 regions, we've got what's called the break-even line. Okay, so what I'm going to want to do is map some industries onto that space. So the first one we're going to look at is the PV industry. So in order to map these industries, we're going to need to know 3 different things. The first thing is the industry growth rates. The second is the energy cost of system deployment, and then the third thing is the capacity factor. So we've seen many graphs like this already, but this is a graph of the growth in global installed capacity for PV. And the only thing I've done differently here is disaggregated this by each of the major different PV technologies. And we can see that currently 90% of the industry is composed of crystalline silicon. The second thing we need is the energy cost of PV system deployment. So here we collected a load of life cycle assessment studies, and we kind of harmonized them all onto an equal basis and looked at them across the different PV technologies. So one thing to note is that thin film is slightly less energy intensive than crystalline silicon in general. But the other thing to note is that these studies, the first one is 1990 and the last is 2011. Now you'd expect that over those 2 decades there would have been some improvement in the PV industry to bring down energy costs. So in order to track that, we borrowed the learning curve model from financial modelers, and we tracked the energy cost, which is this vertical axis, against cumulative production of each of the different technologies. And what you can see is that learning is occurring and it is serving to reduce the energy cost of PV system deployment over time, or cumulative production. Okay, the last thing that we need is to know the capacity factor. So here we used the UN and EIA databases, and on a country-by-country basis looked at the capacity factor of PV systems within each of those countries, pulled those all together and produced this distribution. And we can see that the median is around about 11.5% for PV systems globally. A lot of that is driven by deployment in Germany, where perhaps the situation isn't that perfect for PV. But that 11.5%, as I pointed out earlier, gives this one-to-one correspondence between energy payback time and energy cost. Okay, so if we now map some of these technologies onto this space, here we're looking at single crystalline silicon between 2000 and 2010. So we can see in 2000, the energy payback time for single crystal silicon was around about, well, between 6 and 7 years, and the growth rate was around about 16%. So this technology was sitting right at this break-even line. It was consuming as much electricity to produce new panels as the panels in place were putting out. Between 2000 and 2002, we can see that there is some improvement in the energy costs. So energy costs have decreased because of this learning effect, but also the growth rate has increased now up to about 30%, which means that the industry was then consuming around about 75% more energy than it was producing. And we can see that trend kind of continuing out to 2010. Now if we map the other major PV technologies onto the space as well, we can see a kind of similar trend occurring. The only major different technology is ribbon silicon, which is always within this green electricity surplus region. Another point to note is that the two thin film technologies, CIGS and cadmium telluride, have experienced some incredibly fast growth rates, so up to 200% per year. But they also have a lower energy cost, as I was saying before, which means that they can kind of support that growth rate at a similar kind of fractional reinvestment. Okay, so here are some conclusions. So what we did then was we took all of this information, we kind of projected it out to 2020 and did some sensitivity analysis across all of the parameters. And the conclusions were that the PV industry in 2012, when we did the analysis, was around probably a 50% likelihood that it was at this break-even threshold. So it was consuming as much energy as it was putting out. Around about 90% of its own output it was consuming. But in a worst case scenario, the PV industry would be in energy deficit until 2015, and then wouldn't pay that energy back until 2020. Okay. How much time do I have?
Another 7 minutes.
Oh, perfect. Okay. Okay, so the next thing we're going to look at is the same analysis for the wind industry. So again, we need to know these three things. The industry growth rates, well, we see a similar pattern emerging. And here we've disaggregated between onshore and offshore wind. Here we're looking again at the energy costs, and we can see that wind is less energy intensive to produce than PV. So wind is these three on the end: offshore, onshore, and then unspecified across the life cycle assessment studies that we could find. And then again, looking at the global distribution in capacity factors. And here the peak is around about 25, but what I'm going to do is say that the median value is 23%, which is double the 11.5 for PV. So that then gives a 1 to 2 correspondence between energy payback time and energy cost, which makes it easier to kind of draw out these graphs. So here we see the same kind of mapping of these trajectories for wind, but obviously the first thing to note is that wind is always within this energy surplus region. And this is for the two different technologies, so onshore and offshore wind. So basically, and the reason for this is wind is less energy intensive than PV. It has this higher capacity factor, and so currently is consuming between 5 and 10% of its own production. So it's leaving a lot more net energy available for society. So we've had a lot of talk about storage over the last well, the day that I've been here, but probably longer as well. What happens if we start to add storage into this picture? Well, here, so the main point from this slide is basically that we've got different storage technologies. So I'm going to talk in terms of geologic storage. So we've got pumped hydro and compressed air energy storage, and then electrochemical storage, batteries, basically. So here we're looking, a study done by a colleague of mine at GCEP, looking at again, using life cycle analysis data and looking at all of the energy requirements to build each of these different energy storage technologies. So the first thing to note is geologic storage on the left is very much less energy intensive than producing batteries for the same amount of capacity. Thanks. So when we start to add this storage cost onto the PV technologies, we can see that a lot of them have kind of pushed out. And this is these round circles are the 2012 marker points. And we can see that adding this storage, which is these kind of shaded regions, either geological storage or some mix of all of the storage technologies or just all battery technologies, that's the 3 shaded regions, which you may or may not be able to see there, pushes all of the PV technologies, two of the main ones into kind of more energy deficit region. But when the same thing happens for wind, we can see that it's still within this energy surplus region. So wind can support this kind of storage requirement should we need it to. So the conclusions for storage is that geologic storage is less energy intensive than electrochemical storage, so than batteries, has a higher cycle life, so it lasts for a longer amount of time. Deploying storage pushes some PV technologies into deficit, and wind can afford to buy more storage. So maybe some quick implications. Lower energy costs means that energy systems will cost less money, should do, and they should have lower associated greenhouse gas emissions. And then there's an obvious benefit, as Professor Jefferson was pointing out this morning. Capacity factor is important. It's better to deploy these things in places where they're going to produce more energy. It's also important that we continue to reduce the energy cost of all of these systems. And this should be an explicit goal of technology development, not just driving down the financial costs, but also the energy costs. And then there are obvious benefits. If we're going to start putting out storage, there's obvious benefits to having low energetic cost storage as well. So mainly geologic storage, there's obvious benefits to that. And I think I'll end there. Thank you very much for listening.